All right, here we go. This is the 2017 BC International Exam, question number 6. And we are given the function f of x equals 1 over x squared plus 9. And we're asked to evaluate the improper integral from 3 to infinity of f of x dx and show whether this interval converges or diverges. And I can tell you all right now, we're going to run into a little bit of a problem when we try to integrate 1 over x squared plus 9. At no point in the Calculus BC curriculum have we talked about an integral of the form 1 over x squared plus 9. On the side, I want to go over here. I would expect that anybody watching this video knows that the integral of 1 over x squared plus 1 is the arctangent of x plus c. That's one that we use quite a bit. However, there is a more generalized version, and it's this 1 over x squared plus a squared dx, where a is constant, that we really need here, and it's unfortunate. The integral of 1 over x squared plus a squared is 1 over a times the arctangent of x over a plus Charlie. Since this isn't one that we've talked about in the Calculus BC curriculum, I realize that a lot of the students are not going to know how to find that antiderivative, and that's unfortunate, but we're going to chalk this one up to a learning opportunity, and we're going to add this onto the list of things that we add into the curriculum for the coming year. But let's see what we can do anyway. I think we know from working with improper integrals before that because your limit is going from 3 to infinity, we're going to have to rewrite this. We're going to rewrite this as a proper integral, and we're going to say it's the limit as b approaches infinity from 3 to b of 1 over x squared plus 9, and we're integrating that with respect to x. Now, you may not know how to find the antiderivative, but looking at the College Board scoring rubric, when you rewrite your improper integral as a proper integral using this limit expression, you've earned the first point. And quite honestly, that might be the only point that we earn here, and that's unfortunate, but let's keep going anyway. All right, if you magically knew how to integrate something of the form 1 over x squared plus a squared, then you would be able to do this next part, and you'll say, okay, so this is 1/3 the arctangent of x over 3, and we're going to evaluate from 3 to b. You'll take the limit as b approaches infinity, evaluate, you've got now 1/3 arctan of b over 3, minus 1/3 the arctan of 3 over 3 is the same as arctan of 1. We're letting b approach infinity. As b approaches infinity, b over 3 is going to approach infinity. And what you need to remember about the arctan graph, let me sketch that up here. Your arctangent graph looks like that. You have a horizontal asymptote at y equals pi over 2, and you have another one at negative pi over 2. So what happens as your b value approaches infinity, you're evaluating the arctan of infinity, and what happens is the arctangent graph gets closer and closer and closer to pi over 2. So you're going to have 1/3 times pi over 2 minus 1/3 arctangent of 1. The question you're asking here is the tangent of what angle is equal to 1, and that is pi over 4. Clean this up if you want to. You're going to get pi over 6 minus pi over 12. Because this is a finite number, this tells me that the integral converges. Okay, so to recap, there was 1 point for rewriting your improper integral as a proper integral using your limits. Okay, 1 point for coming up with the antiderivative, that's this part in here, which sadly most folks are not going to be able to do. and then 1 point for coming up with your final answer of this pi over 6 minus pi over 12, which is now 3 points. All right, let's keep going. In part B, we need to determine whether the series from n equals 3 to infinity of f of n converges or diverges. Then state the conditions of the test used for determining convergence or divergence. Well, let me write this out for a second. We're being asked to talk about the series from 3 to infinity, f of n. Well, that is the series 1 over n squared plus 9. Look at what we just did. They asked us in part A to evaluate the integral from 3 to infinity of 1 over x squared plus 9, but now they're asking us about the series. What's the connection between these two? That's the integral test. And the integral test says that if your integral converges, then so does your series. If your integral diverges, then so does your series, provided that f of x satisfies 3 conditions. F of x must be positive. All the terms have to be positive. The function has to be continuous, and the function has to be decreasing. And if I think about the graph of 1 over x squared plus 9, I think it's pretty easy to convince yourself that all the terms are going to be positive. Continuous, well, the only reason 1 over x squared plus 9 wouldn't be continuous would be if we had 0 in the denominator. Denominator can't be equal to 0. As for decreasing, this might be where you want to write down a little bit, but as the x values increase, x squared plus 9 increases, and 1 over x squared plus 9 must decrease. So I would then say by the integral test, in part A, we determined that our integral converges. By the integral test, this must mean that your series, f of n, also converges. And that would do it. Yep. So 1 point for the 3 conditions, 1 point for using the integral test and stating that your integral converges. Now this could be a place, let's say for example that in your integration in part A, you came up with the fact that your integral diverged. And then down here, you said because the integral diverged up here, and all the terms were positive, continuous, and decreasing, that the series must also diverge. I'm pretty sure you would get a follow-through point there. But what I know for sure is that part B is worth 2 points. Let's keep going. Okay. Part C. We need to determine whether the series from 1 to infinity of negative 1 to the n over e to the n times f of n converges absolutely, converges conditionally, or diverges. Now, all those different convergences, what we're going to do is we're going to use the ratio test. The ratio test is a great way to determine convergence or divergence, because at the end you just have to compare. You're going to find your limit as n approaches infinity of the absolute value of a sub n plus 1 over a sub n, and what you're going to do is you're going to compare this to 1. If the limit is less than 1, your series is going to converge. If the series is greater than 1, then your series is going, if the limit is greater than 1, then your series is going to diverge. Well, let's set this up. Limit as n approaches infinity, a sub n plus 1. This is your a sub n term. The a sub n plus 1 just says replace all the n's with n plus 1. So negative 1 to the n plus 1 power, n plus 1 squared plus 9, e to the n plus 1 power. We're now going to divide by a sub n, which is the same as to multiply by the reciprocal. So now we have e to the n, negative 1 to the n, n squared plus 9. Whew. Make sure you get everything written down correctly. And now we start looking for cancellation, and we want to be really careful with this. I see negative 1 to the n in the denominator. I see negative 1 to the n plus 1 in the numerator. Those cancel out and they leave you a negative 1 that you're multiplying by. I see e to the n in the numerator. I see e to the n plus 1 in the denominator. Remember, e to the n plus 1 is the same as e to the n times e to the 1. So those guys cancel. And what that leaves you with right now is your limit as n approaches infinity. The absolute value. Now, the negative 1, we'll talk about that in a second. N plus 1 squared plus 9 divided by e times n squared plus 9. Remember, n is what's approaching infinity. Everything else is a constant. So I'm going to take the limit as n approaches infinity, n plus 1 squared plus 9 over n squared plus 9 times the absolute value of negative 1 over e. Now, depending on how you see this, n plus 1 squared plus 9, you might want to expand that to make it n squared plus 2n plus 1 plus 9 over n squared plus 9. Feel free. The important thing here is that I have n squared in the numerator and n squared in the denominator. These aren't going to cancel, but if I take the limit as n approaches infinity, they're going to head off towards infinity at the same rate, meaning that this limit for this first part of the expression is just equal to 1. So we get the absolute value of negative 1 over e, which is the same as 1 over e, and that's less than 1. Therefore, the series converges. Now, usually when we work with problems like this, you might get that the series will converge for particular values of x. What we're able to get is that our initial series converges by the ratio test. So by the ratio test, this guy here, n goes from 1 to infinity, negative 1 to the n over e to the n times f of n converges absolutely. Okay. So they awarded 1 point for the setup of that initial limit. Then they awarded another point for coming up with your ratio. And then there was one more point for identifying that your series converges by the ratio test. And then 1 point for the absolute convergence piece. 4 points. Not too bad.